This is a gold foil. Okay, gold foil or gold foil, and a beam of alpha particles. A beam of alpha particle, and this is a detector or microscope. Detector or microscope, and we have large angle scattering of some large angle scattering. So backward scattering of very small fraction of very small fraction 1 in 10,000. 1 in 10,000. See here. Okay, let me explain this. So it doesn't take much time. So once I'm done with this Bode's model is there, that's it. Okay, so we are done with the lesson. So okay, Bode's postulate derivation is removed. Derivation only the formulas are required. Derivations are not there. Okay, so that's it. So yeah, see here in Rutherford alpha scattering model or gold foil experiment, there's a polonium. We take cesium or polonium here in the box, lead box. This is a lead box. Why lead box? Because lead doesn't have any reaction, doesn't undergo any reaction with any of the thing. Okay. Now, so what happens here? This source of alpha particle is alpha particles are made to incident on the gold foil. Then what happens is they get scattered in different directions, and then so what happens? They get scattered, and those like this gold foil is of thickness 10 to the power of -6 meter, 1 micrometer, very thin foil, very thin. So gold has a special property called malleability. Malleability means if you can roll in the form of sheets. Okay, so there is photographic plate or a screen, and this is a gold foil. Then what will happen? That is a source of alpha particle, and there are lead chambers. Then there is beam of alpha particle, and we have here this is gold foil. This is a gold foil. So like the source of alpha particles will cross through the lead boxes, so that only we need a beam of alpha particle. We don't want all the alpha particles which are coming from the source. Only beam we want, which can incident on the gold foil. Then the beam of alpha particle, this is gold foil, and this is the screen. It has zinc sulfide, which is also having a detector and a microscope at the end. So to collect the alpha particles, and large angle scattering, you can see backward scattering also. There are some rays, like especially 1 in 10,000, there will be a large scattering, around 180 degrees scattering will take place. Okay, so that is about the Rutherford alpha scattering experiment. So what are the conclusions of this particular experiment? Conclusions and the drawbacks of this particular experiment that we will discuss. Please copy this fast. This is the first diagram. This is the second diagram. Yes, sir. Are you done with the drawings? Yes, are you done with the drawings?
Yes, sir.
Yeah. Okay. Okay, I'll draw one more figure here. The gold foil is like this. So see, that means for the closer the particle deviation is more. This is one head-on collision. This one is head-on collision. That happens one in 10,000. Whereas most of the particle, the closer the particle, the more deflection it will take place. More deviation will take place. The farther the particle, less will be the deviation. Okay. This is the first one. The second one is there is a graph like this. So it tells about this is 0 degrees, 90 degrees, and this is 180 degrees. Here this number of alpha particles scattered. Number of alpha particles scattered. So what happens as the angle increases, scattering angle will decrease. Okay, very few, 1 in 10,000 will undergo 180-degree scattering. Otherwise, almost all are same. Okay, clear? So most of the particles go straight with minor. Okay, I'll write the points also. This one. So what are the conclusions of this experiment? So the conclusion says that the first one, most of the particles go straight most of the particles go straight. Most of the particles go straight through the foil. Most of them go straight through the foil with only minor deviations from and very few with deviation. Okay, with minor deviation. This is the first one. The second one, what he says, alpha particles suffered only small deflection. Only small deflection. Small deflection. Okay. And very few deflected with, and very few deflected with large angles. Large angles. That means 1 in 10,000 will undergo large thing. Okay. So a few alpha particles proceed head-on collision. A few alpha particles undergo head-on collision. So this is about the conclusions of Rutherford atomic model. Now quickly we'll go to the Bode's model. Clear with you all?
Yes, sir.
Okay, good. So are you done with this? Can I go? Can I start Bode's model now? Yes, sir.
Yes, sir.
Okay, chalo. Now, Bohr's atomic model. So according to him, it says like this. See, this is the nucleus, first orbit, second orbit, third orbit. This is a proton and neutrons. N is equal to 1 is equal to K. N is equal to 2 equal to L. N is equal to 3 equal to M. N is equal to 4 is equal to N. Okay. So here the first one is atom is spherical in shape. Atom is spherical in shape. Second one is the entire same. He started with the same. The entire mass of the atom. So the entire mass of the atom is concentrated at the center of atom. Center of the atom called nucleus. The center of the atom called nucleus. Nucleus consists of, nucleus is positive in charge. Nucleus is positive in charge. And nucleus consists of protons and neutrons. Protons and neutrons. And electrons are revolving in fixed orbits. Electrons are revolving in fixed orbits known as stationary orbits. So they have given the name. What is the name? Like every they are revolving in around the nucleus in fixed orbits or stationary orbits. Fixed, what we say, particular orbits known as stationary orbits. Okay. So as the size of the orbit increases, now here fourth one, as the size of the orbit increases, the energy associated with the orbit also, increases. Energy associated with the orbit also increases. So as long as the electron revolves in same orbit, as long as the electron revolves in the same orbit, it neither gains energy nor loses energy. It neither gains energy nor, as long as the electron revolves in the same orbit, it neither gains energy nor loses energy. And he gave the concept that is what? Angular momentum. So he says that electrons are possessing angular momentum. The angular momentum is given by L is equal to mvr, which is equal to nh by 2 pi. He told this. Seventh one. So seventh one, when an electron absorbs energy. So what will happen? When an electron absorbs energy, it jumps from lower level to, lower energy level to higher energy level. Lower energy level to higher energy level. So that is equal to what? See, suppose it absorbs energy. So this is E1, this is E2. So electron will jump from lower to higher. Okay. So that is what? E2 minus E1 equal to h mu. Okay, is that clear? E2 minus E1 is equal to h mu. Okay, please copy this. If you have any doubt, ask me, please. So I can write here delta E. Okay, instead of writing this one, I can write delta E is equal to E2 minus E1. Delta E is equal to E2 minus E1, which is equal to h nu. Okay. Clear? Can I erase the first point here? This one. Can I erase this one? The first point. Yes.
Yes, sir. Yep.
Okay. I'll just erase the first point. So the last point C, or when an electron jumps from jumps from higher energy to higher energy level to lower energy level, it releases energy in the form of light. It releases energy in the form of light. Okay. So, or radiation, we can see in the form of radiation. We can't say light, but radiation. So, because it can be in infrared region also. So, when it is jumping, it releases energy E2, E1. This is h nu. So, delta E is equal to E2 minus E1, which is equal to h nu. This is the formula. Clear? So, this was about, Now, I'm not going to the derivations, only the formulas I'm writing for the radius. Okay. So, for the radius of the orbit, the formula is Rn is equal to Rn is equal to h square n square epsilon 0 divided by pi m e square. Here we have unit radius. It means the first orbit, unit radius, that is A0, which is equal to how much? A0 5.29 into 10 to the power of minus 11 meters. Second, velocity of electron in nth orbit. That is what Vn is equal to E square by 2 epsilon 0 nh. Third one is energy of
epsilon 0 is permittivity of
permittivity of free space. Very good. So En is what? Energy of nth orbit. Energy of nth orbit. The formula is En is equal to minus m e power 4 divided by 8 n square h square epsilon 0. Okay, so that is equal to how much? Minus 13.6 divided by n square electron volt. Clear? So this is the value. So these are the three formulas. Please learn these formulas. Very, very important formulas. Okay, derivations are not there. Only formulas are there. Derivations are not there. Only formulas are there. Okay. So so almost all we are done with everything. Only one hydrogen spectrum is there. That's just I will explain that. Finish. Copy this fast. If you have any doubt, please ask me. Here, h is Planck's constant, n is the number of orbit which orbit. Epsilon 0 is permittivity of free space, phi is the constant, m is the mass of electron, E is the charge of electron. Similarly, here also 2 epsilon, same thing. These are all the constant values. In school, I will be teaching on Tuesday nuclear physics. Okay, finish that only. That I think maximum two classes we can finish of that nuclear physics course. Yes, are you done with this? Yes, sir. Did you complete all of you? This one.
Yes, sir.
Okay. The last one is hydrogen spectrum. Okay, it will take only maybe 3-4 minutes, not more than that. So after that we can leave. Okay. Clear? Can I erase this now? Can I erase this?
Yes, sir.
All of you. Okay. So
Yes, sir.
no. So here the first I will give the spectrum classification. So when you speak about spectrum, right? In spectrum we have classification like this. One is continuous, continuous and discontinuous. Discontinuous. And discontinuous again we have two. What is that? Line spectrum and band spectrum. Continuous, like the best example is like VGR, rainbow. Okay. Rainbow is the best example where all the colors are mixed up. You can't differentiate. Now, in line spectrum, we have fine lines, very, very fine lines like this. In band spectrum, like thick bands will be there like this. We have thick bands like this, okay, in band spectrum. Now, there's about the first one. Next one is what? Last one, that is about the hydrogen spectrum. in hydrogen spectrum, what will happen? See, so example, I'm just drawing this. See here, yeah. So I will draw here. These are the energy levels. Okay. So n is equal to here, n is equal to 1, 2, 3, 4, 5, 6, 7. Yeah. 2, second orbit, third orbit, fourth orbit, fifth orbit, sixth orbit, and seventh orbit. So when you give energy, when you give, the electron will jump to the higher level. It can go to any level. It can go to the second one. It can go to any level, second, third, fourth. So if it is jumping from there, see, it can jump from see, in this way. Yeah. So this line is said to be Lyman series. This is said to be Lyman series. Okay. The second one is what? This is in Lyman series in which region? IR region or UV region?
IR.
IR. Very good. So it is in IR region. Now, if the electron is jumping from third to 2 like this, it can jump from any level. Okay. Depends upon how much energy it has gained. Okay. This is said to be what? Balmer series. This is in visible region, VR. Suppose if the electron is jumping like this. This is said to be what? Paschen series. Paschen series. This is in UV region. The next one is what? Like this. This is bracket series. This is also in IR UV region. And if it is like this, jumping from here to here, it is Fund series. Fund series, which is in again UV region. Okay. So this is about the hydrogen spectrum. Okay, that means hydrogen. Why hydrogen? Problem with Bohr was he could explain hydrogen very well. He failed in explaining helium and all. So hydrogen has only one electron. It can jump to any level. It can jump from ground level to the highest level, or it can jump from. So it is jumping back again, returning back to the first level. That is Lyman. It is returning back to second, Balmer. If it is returning back to third, Paschen. If it is returning to fourth, bracket. If it is returning to fifth, Fund series, like that. Okay. So that is how these series are given. Now, if you see the energy levels, how it is. Every orbit has an energy. So every orbit has an energy like this. So here, suppose n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5, n equal to 6, n equal to 7. Now it is minus 13.6 electron volt. Here minus 3.4 electron volt, minus 1.151 electron volt, minus 0.85 electron volt. Okay, minus 0.54 electron volt. These are the energy. Why minus? What is the meaning of minus? Can anyone say?
You need to give it energy to get it to that level.
No, minus because attractive force. All the electrons are attracted to the nucleus. Understood? So energy of the first orbit is minus 13.6 electron volt, and energy of the infinite last will be 0. Outermost orbit it will be 0. Now I am writing the general formula. Nu is equal to R into C into 1 by n1 square minus 1 by n2 square. 1 by n1 square minus 1 by n2 square. This is the general formula. R is a Rydberg constant. Okay. R is Rydberg constant. How much it is? Rydberg constant.
106 something, no?
Yeah.
Is that centimeters inverse that value, no?
Rydberg constant is 1.097 into 10 to the power of 7 per meter. This is the value. Okay, we can also write 1 by, for visible we write, R is this, based on this there is a numerical in exam. 1 by lambda is equal to R into 1 by 2 square minus 1 by n square. Is that clear? So this is the formula for visible region. Okay. So that's it. Means electron is jumping from where? From this to this. Okay. I write here N2 is greater than N1. Better. You will not get confused. N2 is greater than N0. Keep that in mind. So it will be easy for you. So this completes our lesson finish. So we are done with this lesson. The probably is not there. Okay, so that's it. So tomorrow in next class I will teach a nuclear chapter in the class. Okay. So by that we are at the end of the lesson. Is it clear all of you?
Yes, sir.
So please do solve
Yes, sir.
numerical on this one, on this concept. Radius, velocity, energy, and this one. Four formulas are there. Okay. Is it clear?
Yes, sir.
Okay. Thank you so much. Thank you for your patience and for coming to the class.
Thank you, sir.
Okay.
Thank you, sir.
Yeah, thank you.
Thank you, sir.
Thank you.